Research em Brasil, INPE, em português, Instituto Nacional de Pesquisas Espaciais, em São José dos Campos, São Paulo. Professor Enzo is smart in several fields of condensed matter physics, especially mainly in superconductivity and also in statistical physics. Today he will talk for us about phase transitions in superconductors. The talk is transitions, superconductor-insulator transitions in nanohole thin films. Superconducting ray modeling. Enzo, you have 15 and 1 hour to talk. It's your time.
Thank you very much for the invitation to give this presentation. And good morning to everybody. So I will be talking about the superconductor-insulator transition in nanohole films, a particular system, but actually I will be talking about in more general about superconductor transition in systems which can be modeled by superconducting arrays. And I will, before presenting, and I will present some numerical results for this particular system, which is the thin film with nanoparticles. So the outline of the talk, I will first briefly describe the superconducting array modeling with Josephson junction, then the effects of thermal fluctuation, magnetic fields. Then I will go and to discuss the quantum fluctuations and superconducting insulating transition, motivated by this experimental system of nanohole films. And then I will discuss the model, different models to describe recent experimental data in this system, in which the nanoholes are in periodic arrangement with geometrical disorder and with magnetic fields. And then I will summarize the results. So the Josephson junction array model is basically a system, as illustrated here on the figure on the right top, is an array of superconducting grains coupled by the Josephson effect. So if the temperature is below the critical temperature for the superconducting transition in the grains, the TBCS here, you can have a Josephson effect between the grains. And this Josephson effect is characterized by two equations, the current relation and the voltage relation. The current relation say that between the grains, you can a supercurrent can flow without the voltage, and this current is proportional to the sign of the phase difference between the phase of superconducting order parameter which developed in the grains. If there is a change in phase at function of time, then a voltage develops. The energy associated with a junction, a particular junction, can be retained by a tiny interval of the current times the voltage, and then because the current has a sine sinusoidal relation, the energy associated with a single junction then has a cosine of the phase difference. The amplitude is proportional to the critical current of the junction, and there is a minus sign here. So the minus sign here implies that the minimum energy for a junction is when the phases are the same. So the energy contribution can be extended for the full array, and then you have this the total energy, the total Hamiltonian of the system is a sum of this cosine of phase difference, with the amplitude being proportional to the critical current of the junction, and there is a minus change here, which means that the ground state is obtained by having the phase uniform in both systems. In the original derivation of the Josephson relation, which leads to this equation here, the region between the grains were insulated. But actually, this equation for the energy phase relation is valid in more general situations, in which the region between the grains can be a metal or a superconductor with very weak superconductivity compared with the grains. And the grains don't have to be physical grains itself. The whole thing would be like a continuous superconductor, and the grains would mean local region, larger region, which is superconductivity, and the weak links between the grains could be just a constriction and otherwise uniform, homogeneous superconductor material. So if you now identify the phase of the superconductor model parameter here as the angle of a classical spin with a unit length, the classical spin unit and as indicated here, then this expression for the energy can be written as the scalar product of the classical spins of the unit vector. And the model that you get here is the classical XY model. And in 2 dimensions, this model has a transition which is called the Kosovo-Stauss phase transition. And as you all know, this is a very famous phase transition, and which led to Nobel Prize in Physics for Kosovo-Stauss in 2016. It was the XY model described many different systems besides the superconducting array. So we just mapped it here. He also describes superfluidus, surface growth, melting in any system, and so on. Now, the Kosovo-Stauss phase transition is a peculiar one because below the transition, the correlation function of the phase becomes a power law. And the power law exponent here depends on the temperature. And but right at the temperature, at critical temperature, it has a universal one. So and above the critical temperature, it decays exponentially, and the correlation length has exponential dependence on the temperature, diverge as T goes between C. But this behavior is quite different from the usual transitions, like magnetic transition, in which the correlation diverges the power. So the transition, Kosovo-Stauss transition, is driven by thermally induced vortex, anti-vortex unbind. Now, this vortex, anti-vortex pairs are vortices in the angle of the spins, as indicated here in the figure. Each arrow here rotates around a core, and it can rotate in a counterclockwise and in a clockwise direction. And so here you have a pair of vortex and anti-vortex in the phase. The interaction energy between them is logarithmic, so it increases with the distance for opposite vortices, and those vortices generate thermally at low temperature, are bound in pairs, but above the transitions they are free to move around and give an exponential correlation. So the transition therefore is driven by the unbind of such vortices. This transition in the language of the superconducting rays, corresponds to vortices in the supercurrent, because since the current between the grains is given by the sign of the phase difference, the difference of the phases here leads to a current that circulates around the core of the vortices. So in one direction, the other direction. So the phase transition here corresponded to this unbind of vortices of a supercurrent which circulated around the grain. This transition happened since the transition depends on the coupling between the spins, and this coupling is by itself connected to the critical current for the junction. The critical temperature for the Kosovo-Stauss phase transition in this system is below the critical temperature in which the grains become superconductor. So this transition therefore describes the phase coherence between the grains, which are both below the transition of the grains itself. Between these two transitions, the system has a finite resistivity. Now, these vortices here are created, they are generated thermally. They are not produced by an external magnetic field. Now, if in addition to this, you apply the magnetic field perpendicular to the array, then new things happen. And so the model for adjusted injection rate and external field in the simplest form is to add to the phase difference inside the cosine and a phase shift which is related to the line integral of the vector potential between the two grains. And because the rotation of the vector potential is related to the magnetic field, there is a constraint that these variables here, which are the link variables here, the sum of the little variable around the plaquette, which is rotational over the vector potential around the plaquette, is equal to the flux penetrating that area, and therefore there is this constraint. The sum of these link variables is equal to the, you can write the flux in this form, which is dimensions, where F is equal to the magnetic flux penetrating the plaquette divided by phi naught, which is the quantum of flux or Cooper current, charge to E. Now, this model defines the system in presence of a magnetic field, and the magnetic field creates additional watches, which are given by the whose number is proportional to the magnetic field, and there is a competition between this magnetic field, this voltage-generated magnetic field, and the pinning side of the arrays. The center of each plaquette acts like a pinning side, and the vortex is created by the magnetic field. It can be commensurate or incommensurate with the spinning center. That is give rise to different phase transition. So then, as I just said, F here is the number of flux quanta per plaquette, and is a dimensionless number. And the behavior of the system depends strongly on the value of F. So if F is a rational number, P divided by Q, you can show using a Landau gauge in which the vector potential is, let's say, 0 in the x direction and non-zero in the y direction, that the vector potential depends on the distance in x direction, and the line integral is 2 pi times f, and therefore, if f is a rational number and is an integer, if it's an integer, then you see that this quantity here is just a multiple of 2 pi. And if it's a multiple of 2 pi, inside the cosine, it makes no difference. So when f is an integer, this system behaves as if it has no magnetic field at all. And this is illustrated here on the right. When f is equal to 1, the magnetic flux, the vortex in each, there is one vortex per plaquette. And the current generated by this magnetic flux cancels out inside the sample. There is only a current around the sample. So if the sample is infinite, this behaves exactly like if there is no magnet. Whereas if f is a rational number, p divided by q, then this quantity here will be periodic with a period equal to q, and it will repeat itself. But this will generate couplings in the Hamiltonian, which will differ when f is equal to 0. So in particular, for example, for f equal to 1/2, this gives rise to a phase shift AR, which is equal to 2 pi and pi. So there is a periodicity of the 2 that translates into terms of the vortices of currents as having current have a vortex at each other plaquette, as indicated here by the red symbols here. So for the 1/2 case, we have the double degenerate, which arises because the periodicity, there is a periodicity of 2 for the line integral of the vector potential. So you can also show, using this relation here, that so we just show that if f is an integer, then the system is exactly the same if f is equal to 0. So there is a periodicity of 1. The model is periodic with period 1. And you can also show that there's a reflection symmetry around the 1/2. So if f is slightly above 1/2, it's the same if f is slightly below 1/2. Of course, this only works if the system you describe is perfect periodic. If the system is not perfect periodic, then this periodicity doesn't hold, but it still holds as an approximation. Now, the ground state of the vortex configuration has been studied by this seminal work by Terry and J. Prakash, which show that if you write the Hamiltonian of the system, which was written in terms of the phase, it can also be written in terms of the vortices. And this vortice, as I just mentioned, interact logarithmic. So the Hamiltonian you get in the vortex representation is a sum of all pairs of these vortices interact logarithmically. And the frustration here arises as a background constraint, such that the sum of the vorticity minus f should be equal to 0. This translated into this equation that the average number of vortices is equal to frustration, and the frustration is fixed by magnetic field. This basically is just saying that the number of vortices is proportional to the flux created by due to the external magnet. So if they use this Hamiltonian to find the ground state configuration of the vortices, for example, for square lines. And these are the configurations we find from ground state. For F1/2, we have this one vortex indicated here by plus in every other bucket. And you can already see that it is double generated because you can have a plus and plus diagonal here, or plus and plus diagonal here, no vortex here. And for all the values of F, you have a more complicated ground state, and the generation of the ground state is related to the denominator of this frustration parameter. And as a result of these different ground states as a function of F, there's a sharp variation of the system, behavioral system as a function of the magnetic field. There are, in fact, different transitions for different values of F. The case which has been mostly studied, besides the F equal to 0, of course, but that's the case, that's basically the Pesquisas transition, is the case of when the frustration is equal to 1/2. And for this case, since the ground state is double degenerated, as illustrated here in the figure, in which the plus indicate the positive vortices, the minus the negative vortices, which are the here. And there are two excitations of the ground state. You can have this, you can flip one spin around to the other direction. I mean, you can identify this with a spin, so that you can flip the sign in one point, flip the sign at another point. So this corresponds to a vortex pair in a background which it has roughly zero vorticity. But you can also have defects like domain walls. This is a closed domain wall. So there are two kinds of defects for this case. And therefore, there are two possible transitions. You can have a Pesquisas space transition, which is associated with this vortex pairs, or you can have a nice transition associated with this domain wall. And it turns out that the transition in the system is has been studied exactly because of this triple possibility, and the transition seems to happen very close together because the Pesquisas was slightly below the other transition. This has to be studied by many people. I guess indicates some reference here. Now, since as just shown, the ground state is a strong dependent on the frustration parameter. The critical temperature obtained by Monte Carlo, as indicated here in the figure on the top left, is a strong dependent on the frustration. And as we can see here, the TC is open symbols here. Is strongly dependent on the frustration, and the critical current of the they also depend strongly on the frustration. It has the critical temperature is larger for zero field or field equal to or zero field or integer frustration, which are equivalent. And then the next highest one is 1/1/2. The next one for 1/3, and so on. As you lower the temperature, as you have a more and more transition happening. They were also able to show a relation between the critical current and the ground state energy, and the critical temperature and the ground state. Since the ground state energy, although it depends on F, it depends weakly on F. This relation here that shows that the critical current and the critical temperature strongly depend on the denominator over the rational number, which describes the frustration. It is strongly dependent on the rationality of this frustration parameter. In particular, if you have a rational number, which can be represented by a rational fraction with a very large Q tends to 0, this equation suggests that the critical temperature vanishes for a rational number. So that was a question in the raised during this work, and there were many other calculations, many numerical simulations mainly, and it appears that this system actually at the rational frustration, the vortex lattice is incommensurate, and the critical temperature is 0. So there is no phase transition at finite temperature. On the left here, we show what you would expect for the resistivity as a function of a frustration, a function of magnetic field, the parameterizing the frustration, because of this dependence on the critical contact, change rapidly with the frustration. As you decrease the temperature, first you get a minimum at the integer value of frustration. Then you get a minimum at the 1/2 frustration. Then a minimum at the 1/3 and so on. There are more and more minimums as we lower the transition. The same thing happens if you are at a 0 temperature and you decrease the current from a large voltage. First, the voltage shows a minimum at the integer values, then at the 1/2 value and so on. This particular picture here is for the square lattice, which you just suggest, but there is a strong dependence on the geometry of the lattice. And for the honeycomb array, for example, the behavior at frustration 1/2 is very peculiar. For this case, the vortex spinning centers, which are on the center of the plaquettes, the so-called jewel lattice, from a triangular lattice. We have the nodes of these lines here would be the location for the grains. And the center would be the center of plaquettes, but you see the center of plaquettes from a triangular lattice. So if you have a frustration, it's 1/3. If there is one vortex per 3 plaquettes, then you can find there is a ground state that matches the pinning size. And in fact, this situation here is the 3-fold degenerates, and there is a transition at finite temperature. But if the frustration is equal to 1/2, then you have a geometrical frustration. The ground state is macroscopically degenerate. There's a very large number of ground states configuration which have the same energy. And the geometrical frustration arises because if you identify the occupation of a plaquette with a vortex by a spin 1/2, if a vortex is located in the plaquette, you call it plus 1/2. If it's absent, we call it minus 1/2. Then, since they are located at the center of the plaquette, this is actually similar to an antiferromagnetic Ising model on a triangle lattice, which has a frustration because if you have the spins, if you have, say, one spin up, the next spin can be down because the interaction is antiferromagnetic. But then the third one cannot, the energy between the neighbors cannot be satisfied because if you satisfy one spin, you cannot satisfy the other. As a result, there is a ground state that generates, which is similar to the ground state that generated by the model. The models are different. But this suggests that the critical temperature for this case is also zero. And this has raised an interesting question. There were many works done on this problem. There are different calculations. There are suggestions that there was actually a Costas-Thales transition at finite temperature. And also someone suggested there was a spin glass transition, although there is no disorder in this case. And there was also the later calculations, as far as I know, actually indicated that there is no transition to finite temperature. There is a 0 temperature transition, but the correlation lengths diverge as you approach 0, which is a different frequency point. Now I will show here some of these experimental systems which can be modeled by this superconducting array radius injection. On the left top here, is one of the early arrays, which are superconductor-insulator junction, SIS junction. And you see here the resistivity, the resistance of function of frustration, which is the already parameterizing for the frustration magnetic flux. So the plaquette divided by quantum flux, and you see minimum at the interval and secondary minimum at 1/2. There's another one that you can actually see more high order values at the odd minimum at the high order commensurate states, besides the commensurate states at the interval. This is one in which you have a superconducting range on a metal, so it's a superconducting normal to superconducting junction, and you also see many oscillations. Those two are actually superconductor-insulator superconducting junction. And here is another system, which is a system that I will be describing here, in which you have a film with some nanoholes. So there are no real physical grains in the system, but we have holes. So the system is multiply connected. But again, you see here is still the function of frustration, has a minimum at 1/2, and the secondary minimum at 1/2. The primary minimum at the interval, and are very high order minimums here. This is a square out of holes, and between the regions which are large here, you can regard this system as made out of superconducting arrays with constrictions. So there's a constriction between one plaquette here and the other plaquette here, and you can model this thing as a square array of a junction. Here on the right, you have a honeycomb array with holes located on a triangle line. And again, this can be modeled as an array, but now because the holes are located on a triangle line and the holes are at the pinning side, then this is the appropriate model for this one is an array on a honeycomb line. In both cases, you can see minimums as a function of frustration. This is another system which has also a triangular array of holes, but you cannot see here in the figure. There's a triangle axis of 300 nanometer nanoholes. This is a high-density superconductor, and there's a function of the magnetic field. Here they didn't parameterize in terms of frustration. It's in terms of magnetic field, but you can parameterize in terms of frustration. There are minimums which occur at the interval of frustration, but if you look carefully here, there's no minimum at frustration 1/2 because this is a triangle axis, similar here, which is consistent with what we mentioned before, that for the honeycomb array, it's appears that there is no transition from temperature. Now, I would now like to concentrate in the system, which is the main focus of the presentation, which is the superconducting slate transition arrays, and in particular in thin films with the triangle axis number. This has been motivated by this experiment done by the group of Stewart at Brown University, in which they studied these films which are produced by depositing the film on a template. The template is sketched here on the left. This is an aluminum anodic oxide substrate. The film is deposited on the template, and the film takes the form of template, but with height variations. There are large bumps for the nodes of this substrate, and therefore the bumps form a honeycomb lines of regions. And if you study the resistivity of this system, with a function of temperature and thickness, as you decrease the temperature, there are some samples the resistivity tends to go to 0, while other samples the resistivity increase. And as you decrease the thickness, therefore there is a superconducting insulator transition for some particular critical value of the thickness. Now, in the insulating side, for example, sample 6, if you look for the resistivity as a function of magnetic field, this figure here in particular is for 0 field. If you now apply a field and look for the resistivity of the sample above in the insulating phase, you see that this resistance oscillates. And the oscillation has a period of 1 flux quantum per plaquette. And this is you can translate this in terms of frustration or filling factor, if you wish, which is the flux in the unit cell of the array divided by the quantum flux. And the quantum flux here is the quantum flux of Cooper curve. So therefore, this oscillation is a function of a magnetic field with a period equal to the quantum flux for Cooper pair, indicating that this insulating phase is actually Cooper pair insulated. And that's one of the reasons why this particular system has been, this particular geometry for pyramid with nanoholes has been used with the superconducting insulating transition, because you can actually identify the superconducting phase, the insulating phase, if it is made of Cooper pairs, bosons, or if it is made of usual electron insulator. If you now this resistivity in the insulating phase oscillates as a function of field, but if you look as a function of a temperature, you see that as you increase the temperature, this oscillation, of course, decreases in amplitude, but the value of the resistivity decreases. Right? So that because you are in the insulating phase, the resistivity, the resistance increases exponentially with temperature, with an activation energy. This activation energy depends on the distance between the transition, and it decreases as you approach the transition point above. Plotted here on the right is this activation energy, therefore, as a function of distance from the critical point here meaning the critical thickness, and the behavior is slightly different for F equal 1/2, for stage 1/2, than for F equal 1/0. We're going to come back to this point, and to describe the system, we have to add additional terms to the Hamiltonian. So the Hamiltonian so far that we have described was a Hamiltonian that only takes into account the Joseph coupling between the grains. But if the grains are sufficiently small, or the superconductivity is weak, you also have to take into account the fact that the grain has some size. And if the grain has some size, it has some associated electrostatic energy. So the electrostatic energy is the total charge in the grain divided by the capacity. Now, the total charge in the grains is given by the number of Cooper pairs in the grain. Actually, the deviation of the number of Cooper pairs on the average value, which is cancelled by the background charge. And this term is written here. So the Hamiltonian now has two terms. This is the simplest possible Hamiltonian you can write to take into account this effect. And this Hamiltonian here leads to a superconducting insulator transition, as shown by Donian a long time ago. The first time here, the charging energy can be written here, therefore, in terms of n, which is the number of Cooper pairs. But the number of Cooper pairs is a canonical conjugate to the phase. So it's an operator. So both n and theta are operated. And they satisfy a computational relation, which is written here, which is the analog of a momentum and position computational rate for a particle. So when the phases are well defined, the charges are not well defined. And when the charges are well defined, the phase is not well defined. So this leads to superconducting insulator transition, as sketched here on the figure on the right, which shows a typical superconducting insulator transition in some of the system as a function of temperature, and the parameter here, which is the ratio of the charging energy divided by the Josephson coupling. The charging energy here being related to the capacitance of the grain. So the critical temperature, which is for F equal to 0, there's no magnetic field. The temperature here, the critical temperature at the zero charging energy here, which would be a phosphorus Taurus transition, as you increase the charging energy, decrease, and eventually goes to 0. And at 0 temperature, there is a superconducting insulator transition. If you add a field, then the transition line will change. And in particular, as we just mentioned for honeycomb line, there is no transition at the 0 field. at the zero charging energy. And so the transition line here is actually, at the moment, is unknown. Now, as I just mentioned, because there is a computational relation between charge and phase, there is an uncertainty principle. Right? The uncertainty states that you cannot measure the phase and the number of Cooper pairs here simultaneously, and this has leads to superconductor-insulator transition, which is nicely sketched here. So in the phase coherence state, in which the phases are well defined, then the number of Cooper pairs in each grain is not well defined, because the Cooper pairs can hop from one grain to the other one, and so the system is a superconductor, and the resistivity is non-zero because the Cooper pairs can flow around. In the phase incoherent state, when the phase is not well defined, then the number of Cooper pairs in each grain is well defined. So the Cooper pairs are localized in the grain, and there is an energy cost for a Cooper pair to move to one grain to the other one. This energy cost is roughly equal to the charging energy if you are far away from the transition. And so this system is an insulator. So now this phase transition, the superconductor phase insulator transition, has a second order phase transition, which has its own critical exponent. And there's a scaling theory that describes this transition. The scaling theory for the superconductor transition states that, well, there is a critical value for this ratio of the charging for the Josephson coupling, where the transition occurs between superconductor and insulator. There is a divergent correlation length, which depends on the distance to the critical point, and the measurable quantities or observable should scale with this correlation. So in the superconducting phase, the phase stiffness is finite. The phase stiffness measures the stiffness of the phase coherent state, the energy cost to actually untwist the phase. And this phase stiffness here, from scaling theory, scale with the correlation length, and you can show that it vanishes as you approach the transition temperature. Delta G here is the distance to the critical point. Eta Pro vanished as opposed to the critical coupling of superconductor installation with this exponent here, which depends on the correlation length exponent and the dynamic exponent D. In the insulating phase, the energy gap for the insulator has this dependence on the distance to the critical point, and it vanishes as you approach the transition point above. Now, right in the transition, the conductivity can be related to the phase stiffness divided by frequency. And from the scaling theory, you can show that the frequency-dependent conductivity is scaled with the power of the frequency. And the exponent is the dimension of the system minus 2 divided by the dynamic exponent. For in the 2-dimensional, which is the case we are considering here, d is equal to 2, so the exponent is equal to 0, so this is the constant. So that means that the conductivity is a universal value, has no dimensions. And so it is an intrinsic quantity for a particular phase transition that doesn't depend on the details of the model. So this quantity here has been measured experimentally and also obtained numerically, both analytically and by numerical simulation. And for the array problem, for the superconducting array, as maybe it's not surprising that the results will depend on the frustration problem. And as shown here, is different. For frustration equal to 0, there is 0 magnetic field, or then a magnetic field corresponds to 1 flux quantum per cell. On a square lattice, this conductivity in units of the quantum conductivity for a Cooper pair has this value here. That's what obtained by numerically and analytically. And for F equal 1/2, the result is different. And you see it's almost twice as the value for 10 for the zero field case. And these have been shown analytical and numerical. That's particularly interesting because usually the universality class has different exponents, but the exponents do not change that much. But here, this quantity, which is dependent on the critical point, changes by a factor of 2. And this is for the square lattice. Sorry, this is for the square lattice. For the honeycomb lattice, is what we're going to discuss next. So the numerical results which I will present are based on this numerical simulation with the path into representation. The path into representation allows you to map the model into a quantum mechanical model into an equivalent classical model with an extra dimension. So for the model we are considering 2-dimension, you map it the 3-dimensional model on a layer in which this extra dimension is the imaginary time on the path interval transformation. So the model that you get with path into representation has this has the contribution here with the Josephson coupling, and the contribution from the quantum fluctuation of the charging energy get mapped into the coupling in the imaginary time direction. So it becomes a 3-dimensional model. But the quantities here are not operators; they are classical. You can use Monte Carlo, traditional Monte Carlo simulation, to do the calculation. And the mapping show that there is the problem here is a classical problem in which the effective temperature is the ratio equal to the ratio between the charging energy and the Josephson coupling. The correlation length is different in the time and spatial direction. They are defined by an exponent z, which is dynamic and exponent. And the energy gap in the insulated phase is related to the inverse of this correlation length. And the ground state energy of the quantum problem is related to the free energy of this classical model. So we could use this method to perform the numerical simulation. So if for the superconductor insulator transition for periodic array, then the appropriate model is a model on a honeycomb lattice. If the system is a triangle array of holes. If it is a square array of holes, it will be a square lattice. And we are interested in particular in the measurement done for this system here, which they show some interesting results. And the calculations for the critical coupling for the transition are shown here. You see that there is strong dependence on frustration. The critical coupling is larger for zero frustration and into frustration. There is but there is no the main figure here is for the honeycomb array, and for comparison we also show for the square array. And then you see that for the square array, the next high temperature is for 1/2, and then for a third, and so on. But for the honeycomb lattice, there is no maximum at 1/2, which is actually what you see experimentally. Okay. So in the insulating phase, the energy gap vanishes as we approach the critical temperature, and you can calculate the critical exponents. And one finds that for zero field or zero frustration, the exponent is different from 1/2, showing that they are in different universality ones. And here we show the behavior of the energy gap, just above, just slightly below the critical coupling for zero field. And then you see that the energy gap increases and then decreases. There is no feature at 1/2. There is a feature 1/3, which is what you see experimentally for the activation energy. There is a oscillation. There is a maximum here. There is a minimum at integer value, but there is no minimum at 1/2. For the square lattice, you should see a minimum. But as far as I know, there is no experimental data obtained for the system yet. One can also calculate the universal conductivity at the critical point. So the conductivity is related to the phase stiffness, and then you have to take the account that the system is finite, and they use a finite size scale to extrapolate to zero frequency limit. And this has been explained in this paper in detail. And when you analyze the data, you find that the conductivity at the transition is for this model is 1.29, which is quite different from what we obtained for the spread out. It's actually a factor of 4. So for every 1.5 in a honeycomb lattice is very different for every 1.5 for a spread lattice, and it's also different from zero field case. So they are different universality pairs. For the zero field case, the number, the critical, the conductivity that transition is the same as for the spread lattice, but for the 1.5 case, it's not, because it depends on the structure. Now I would like to consider some experiments, some data, some experimental data realized in the same system, in which now the honeycomb array does not has some geometrical disorder. Here, as illustrated here in the figure in the left. In the top figure, there is almost not perfect, but almost periodic lines. But the yellow lines here is a Voronoi construction to obtain the areas associated to each of the holes. And the area is almost constant. I mean, this is the probability distribution of the areas is very sharp. Here is a sample in which you are constructing in such a way that the holes are located in different positions, but they are, so the areas around each holes are different. So if you look at for the probability distribution of the areas, you see the distribution is very wide, so there's a lot of disorder with it. So they compared the two systems, and they were particularly interested in what happened to the superconductor-insulator transition for the system, and in particular, what happened to the resistivity at the transition. How universal is this transition? Or if it's not universal, how it depends on disorder. And this shown here on the figure on the right. There is the figure on the top here is for small disorder. This is the sample on the left figure. And the next figure is when the disorder is large. And here, the resistivity is a function of frustration. Just above the transition in the insulating phase, it oscillates as a function of frustration, as we'd expect, with minima at the integer values. There's no minima at 1/2, because, as we just explained, it's probably due to the fact that it's a honeycomb array of grains, so it's a triangle of holes. And if you look as a function of temperature, here there are 3 temperatures. Each line in different colors means different temperature. The red one is higher temperature, the blue one is a lower temperature. And you see if you change the temperature, the line cross at a particular value. This crossing point here is an indicator that there is a superconductor-insulator transition driven by the magnetic field. And so from the crossing point, they can estimate what is the resistivity after this, after the transition. And they find 2 things. They find that first, they find that the oscillations here that you see the function of frustration decreases in both the amplitude, as a function of frustration. And they also find that they disappear above some critical value of frustration in terms of disorder parameter, which they define as being the average frustration times the disorder associated with the area. So there's an effective flux disorder in the system, which is the product of the average frustration times the disorder in the areas. So they find that oscillation disappear roughly when this parameter here is around 0.3. Now, if you look at the resistivity at the transition, with the crossing points here, as a function of this parameter, the disorder parameter here, you see that the resistivity here for a small disorder is close to the value of the sample without disorder, of course, but as you increase, it increases the disorder, it increases until it saturates some particular value. So there seems to be a dependence on the disorder, and eventually it saturates a particular value. The ratio between the value that's saturated by the value at zero field, this is around 1.8. So this data motivates us to look at into the model, to look at the modification of the models, which would describe this experimental data. And the model we consider to describe the system is again the model is a charging energy, but now we allow for the vector potential to be written as a contribution which comes due to disorder. So we consider model in which you can model in which the grains are still defined on a honeycomb lattice, but the area which plaquette gives rise to different flux. So then we can consider model in which the grains are located on a honeycomb lattice, but the flux in each grain changes. So there's a random flux on one side to the other. And that's a particular way of defining the model that is convenient, especially for numerical projects. So then the line integral on the one grain to the other one, it has a contribution from the renders of the flux. Then it can be rated as the vector potential if there is no disorder, plus an additional contribution, which is written here as Tij. So this is the vector potential with the two terms, which is uniform as a term which is random, and when one has to use a particular model for this random term. And sorry, and you immediately find here that the flux so a plaquette, which is lining into the vector potential, then therefore it has two contributions. It has a contribution from the uniform array and a contribution from the randomness. And the contribution of the randomness of the areas can be written as the average flux times the average times the deviation of the area, the randomness of the area. So this is the origin of the effective disorder in the system. It's a product of the average magnetic field times the disorder of the area. So you can actually change the disorder by changing the magnetic field, even for a sample which has a well-defined disorder in the area. So this quantity is strength of the disorder. So now we use this model and perform numerical calculation as a particular disorder in the represented disorder in the areas. And this is on the right is the results for the critical coupling as a function of disorder, affective disorder, and the red line is for a frustration 1.6, which is close to the critical point for the transition of the stereo experimentally for the magnetic field induced transition in the system. We also add a calculation for the case in which the average frustration is integer, and you see the behavior is different. It increases for a high order rational value and decreases for integer value in merged at a particular point. The point which we merge here is related to transition to a glass space, in which the disorder is so large that the vortex is introduced by magnetic field in a disorder region. And this can be shown by calculated critical current and temperature. If you look at on the right here, we show the energy gap just above the transition as a function of frustration, and you see it oscillates as a function of frustration, as you see experimentally, and disappears at a particular value of the frustration, and then which is similar to what you find experimentally. And now here we compare with the experimental data. So the numerical simulation show that magnetic oscillation disappear at a particular value of disorder, which when you convert it to the experimental system is very close to what you see experimentally. And the increase of the resistivity at the transition compared with the zero disorder is very close to what we see experimental. We find 1.8, here we find 1.3, but regarding consider the Europa, they are very close together. And so there is a good agreement between experimental and theory, showing that this modeling will describe the system reasonably well. Now, I still have, I'm close to the and so this is the phase diagram you obtain for this phase is illustrated here for into the field.
Enzo.
Yep.
Enzo.
Yeah,
increase your voice. Your volume is not so good.
Oh, I'm sorry. So you should have.
No. Okay, just talk close to the microphone.
That's almost at the end, but you should have. But anyway.
No. Go.
It's fine. So the phase diagram will be taken for this phase here, and this is from the left is for the interdecays, and on the right for the non-interdecays. They are qualitatively similar. There are three phases: superconductor, vortex layers, and insulating phase. And the notable difference is for a small disorder, in which for the interdecays, the critical property decrease with the disorder, whereas for interdecays, it increases the disorder. But they both mirror that same property. And for this particular calculation, we use a particular kind of disorder, a particular distribution of the disorder. But when the disorder is very large, which is the limit to the right here, models with different disorder should roughly give the same result. And so we have done a calculation using different kind of disorder, like a random flux model, engaged Bayes model, phase Bayes model. And these are the calculations. I will not go in much in detail. They all give us similar results. I will now like to the last application, which I want to describe, which is the case in which this nanohole film has some Stokes magnetic theory. This is the same system, the same group, and this again, the same figure that I showed before. There is a superconductor-insulating phase, which I just described, with with and without disorder. And here just a summary of this, what happened in the system. So there is a superconductor-insulating transition at the zero temperature, and just to fix some ideas here, if you are in the insulating phase, if you have, let's say, two samples, sample 1 and sample 2, the activation energy measured in resistivity measurement, the factor temperature, which is indicated here, the activation energy here now, call it T naught, we call it U before. Is the activation energy. This activation energy is in the model is associated with the energy gap, and this energy gap depends on the distance of the transition, as we mentioned. So T naught depends on the distance to the transition, and therefore, if you have two samples, one sample that is closer to the transition, and the other sample that's far away from the transition, the sample with far away from the transition should have a high activation. And similar, if for the same sample, if I apply a magnetic field, 1/2, the activation energy should increase since the distance to the transition increases. Instead, you find something different. This is what they find experimentally by doping the system with magnetic impurities, gadolinium here, during the growth process. Magnetic impurities reduce the pair breaking energy of the superconducting molecule, and therefore should decrease the critical property, because therefore the effect of magnetic impurity should actually is to move the boundary for the superconductor-insulator transition to the left. But so the activation energy should increase both for zero frustration and for 1/2 frustration. Instead, what we found is a non-monotonic. So here is the activation energy as a function of a concentration of a magnetic impurity. And for zero field, we have to zero here, the activation energy first increase and then decrease. For after 1/2, it's increased slightly, decrease in the all mirror at some particular value. So to explain the results, they model the system as an array of doses. and but made some approximations, and they explain the results by the effect of impurities, magnetic impurities on both Josephson coupling and the capacitive charging tension, which is, and this is to the fact that the magnetic impurity changed the reduced the power breaking, and therefore they affect both the Josephson coupling and the charging end. So the activation energy here, which is depend on the distance to the transition, has two terms. The first term here is essentially charging energy, but here renormalized by the effect of magnetic impurity, minus the Josephson coupling, which is also renormalized by the effect of impurity, times a function which describes the critical coupling for the superconductor-insulator transition. And using this model and with some parameters, they were able to find a behavior which resembles the experimental data. Here is the activation energy as a function of the concentration of magnetic impurities for F equal to 1.0 and F equal to 1/2, and for different samples, and which do resemble the experimental data in some way. It has a non-monotonic behavior, but it lacks the merging at some particular point. So the curves do not merge in this particular model. So we were particularly interested in this behavior and want to describe the array model with some modification and describe the experimental close included this merging of this transition. And for that, we use again the same model we used it before. But there is no magnetic flux disorder, but there is a disorder in the junction itself, because the magnetic impurities, which are deposited in the gross cross sections, they can fall inside the junction itself. And the magnetic impurities in the junction can induce a phase shift of pi in the Josephson coupling. So a phase shift of pi here is equivalent to having the Josephson coupling negative. So then we can model the effect of the junction by considering an array with the effect of magnetic frustrations, which is also called pi junction frustration, by a fraction of x of negative junctions, which increase with the impurity doping. So the increased impurity doping increases the number of negative junctions, which leads some important effects I will just describe. Now, the model is the same, except that now Aij is equal to 0 pi. And the fact that the coupling is not going to be negative leads to frustration effects, even at 0 field. Even there's no magnetic field here, you still have frustration, because the number of negative junctions in a plaquette is an odd number. So this can give rise to a circulating current in the plaquette, even though there's no external field. And since this junction can be, negative junction can be in different phase, this current loops can be in different phase. So there's a kind of glass circulating. So the frustration effect of pi junction located random leads to a circulating current opposite polarity, which act like Eisenlike or the spin glass or the polarity. So this polarity can be defined as the circulating current of around the loop, and this is the sum of currents of each junction, and the circulating current is induced by Kawamura, which are the panel glass in superconductor. But here is a case in which you have a quantum fluctuation of the panel glass. So the question arises if there's a possible chiral glass space for large disorder, and if this chiral glass space is a superconductor, an insulator, or something else, like an anomalous band. So we perform calculation in this system using definitely quantum simulation again. And here is just an illustration of one of these calculations for a small fractional disorder, a small fractional impurity. with more fractional impure, you still expect there is a superconducting insulator transition. And here we look at the phase stiffness behavior, and as we show here on the left, there is a phase transition which can be identified by the crossing of the phase stiffness for different system size, from which you can get the critical exponent, and you get a critical exponent here for 0 field and for 1.5 different for each other. So they are indifferent universal effects. So at small disorder, there is still a superconducting insulator transition, and the effect to 0 at the 1.5 are indifferent universal effects. Now, if the disorder is very large, so for larger disorder, the system is in a glass phase, the color glass phase. So the appropriate quantity to look at is the Edward-Anderson order parameter, and this is illustrated here. The Edward-Anderson order parameter, the finite size scaling, can you use it to describe the data is written here. From that, you can get the critical exponent. And you can also look at the phase stiffness, which is a measure of the superconducting to insulator transition. And from that, you find that there is a color glass to insulator transition. And this color glass, so there's a color glass to insulator transition, and there's a superconducting to insulator transition. And the critical coupling for both the color glass and the superconducting to insulator transition are very close together, actually within the error bar. So the color glass insulator and the superconducting insulator transition happen at either the same temperature or at temperature very close together. So the phase diagram will be obtained by varying the doping, varying the concentration of impurity is illustrated here for 0 field and for 1.5 field. And there are 3 phases: superconducting, color glass, insulating phase. They are qualitatively the same, but again, the difference is that for a small disorder, for 0 field, the critical coupling decreases and before reaching a plateau, whereas for 1.5, it increases before reaching a plateau. And this is for the square lattice, but for the polycomb array, this is more clear. So here I plotted the critical coupling for 0 field and for 1.5 respiration as a functional disorder, and see the critical coupling decrease for 0 field, increase for 1.5, the inversion is a particular point. And this particular point in which the inversion is the entrance into the color glass phase. So the color glass phase is a superconductor. That's the critical point of the result of this calculation. What a consequence of the fact that 0 field and 1.5 respiration behave differently is that if you look for a sample just above the critical coupling for superconducting insulator transition for 0 field, then and look at the energy gap as a function of disorder, and you see that for 0 field, this energy gap increases, whereas for 1.5 it decreases until the inversion is some particular point. And this you can now compare with the experiment. And in order to compare with the experiment, we have to take into account the fact that the Josephson coupling and the charging energy also depend on the period concentration. So we can go back to the model used in the experimental work with the activation energy has 2 terms, but with some modification. In this model here, the first term was the charging energy normalized by the impurity concentration, the Josephson coupling, and the function F here was assumed to be a constant. But F here actually is the critical coupling for the transition, and as we just saw, this critical coupling depends itself on the charge on the period concentration, on the period doping, being different for 0 field for 1.5 case. So if you take this into account, you replace this function by this behavior here, you have the results shown in the figure as the main figure here, and for 2 different samples. For 0 field, it increased monotonically and decreased for the inversion at a particular point. And this is much closer to the experimental data than the simple model that we described before. So this modeling seems to describe the data with magnetic field, and moreover, it indicates that the point at which the curve merging here is a transition in the chiral gas phase, which is a particular interesting phase. So with this, I would like to just show the last page, which is a summary of the results. And so we went ahead of time. I will just thank you for listening and ready for questions.
Thank you. Thank you, Enzo. Thank you for your very good explanation of what you have shown for us several very nice results. And so I will call people here to ask you some questions about your talk. Thank you again, Enzo. And as yesterday was the International Day of the Woman, the first question will be done by Professora Laura. Profesora Laura, are you here?
Profe, ¿cómo está? Laura es la que se encarga de hacer todo el proceso de redes de la Universidad Nacional de Colombia. Ella es Diana.
The word is with you, so, Ximena. Your time, Ximena.
Okay. Thank you, Professor Isaías. Well, that was an interesting talk, but in this case, I don't have any question. And I will, let me see, here in National University of Colombia, we don't have question also here for Professor. Thank you very much for your talk. Yeah, for an interesting talk. Thank
you.
Okay, thank you very much, Ximena. And Profesora Blanca Rojas.
Hola, felicitaciones por la conferencia, pero no tengo preguntas.
Muchas gracias.
Excelente su inglés.
Profesora Rita. Rita, are you here? No? Okay. Okay, Rita doesn't have questions. So, Professor Stewart.
Thank you, Enzo, for your talk. Very interesting. A lot of material. I have some questions. You never mentioned the word hopping. I was hoping you would mention the word hopping. So on the insulating side of the transition, you seem to show the so-called gap, the mobility gap. Do you ever see a transition to hopping conductivity, which would have a different temperature dependence in the insulating phase?
Well, let's see if I actually show here it's probably mean this figure here, right?
This I have a question on this one as well, but just in general, does the insulating phase not involve hopping transport? Is it just a gap?
Well, in the calculation that I do, the whole calculation is done at zero temperature. So I only find the insulating phase. I cannot actually. So the energy gap that I find that is the energy for the mobility, as you said. So it's the energy for the insulator. So it is a true insulator in this sense. But I think there are situations in which you for the superconductor insulator transition that the insulating phase is a localized insulator, and for that you actually find this hopping conductivity. But those are. This system here and the phase transition that I'm describing between superconductor and insulator. So there's a Mott insulator. That's why there is a
yes.
But I think there are systems in which you actually see a transition from superconductor to an insulated phase with a localized insulator. And that's the case, I think, is one of these, I think the vortex glass, which they see if you have like a superconducting film with a strongly disorder in a magnetic field, and then the insulating phase can be actually a localized insulator, and then you have hopping conductivity. And the hopping conductivity, I think, is a nominal of that. You have a different exponent.
I mean, in the hopping mechanism, the prefactor for the conductivity is quantized. So for MOT, it's 2e squared upon h. So it would fit in with your.
I see. But then the hopping conductivity is not thermal activity.
It does have a temperature dependence.
No, but it's not thermal activity. It doesn't have an exponential behavior.
For variable range hopping?
Yeah, it doesn't have an exponential behavior. It doesn't have an activation exponential of something. Because here, you see here in the figure, here the resistivity, which they find, is proportional to the exponential of U divided by KT. So the U is the activation energy for this system. Yeah. And so this is the quantity which I can infer from the calculation.
Yes.
Now, for variable range of hopping, for example, you don't actually have the exponential behavior. If I remember correctly.
You have something like that, but it's t to the for MOT, it's t to the 1/3.
Right. It has an exponent. It has an exponent there, but it's not thermal activity.
Yeah,
because the process is different. There's no gap.
Yeah.
And so it's because it's hopping at different distances, and that gives rise to this particular behavior of MOT behavior, but it's not a MOT insulator.
No. Okay. In the graph you have here, you're plotting the independent variable is the thickness of the bismuth. Now it's in the region where it's related to the de Broglie wavelength. Is it just the quantum effect? Is it just a quantum effect that's coming?
It's a quantum effect. Yeah, it's
just a quantum effect.
Yeah. So the transition is essentially because of the quantum effect. I mean, in this model here, just because you have this first term here. Yeah, if you don't have the first term, then you just have, if you go to very low temperature, then, if there is no magnetic field, then all the phases are uniform and you get superconductor. But then if you take into account the charging energy of the grains, then eventually this term dominates over the other one because you increase the EC. And then that's why you get this multi-insulator transition, the superconductor multi-insulator transition. The interesting aspect of this particular system here is that there's a question if the superconductor-insulator transition in any of the systems that you see films, for example, if this transition can be described just by a bosonic model, in which you only consider bosons which are superconducting and then become localized, like with hopping that you said, or there is a MOT gap or something like that. And there's another possibility that the transition is actually is due to electron, to free electron localization. And so this is difficult to distinguish experimentally. In this experimental here, using the nanoholes, they can actually ensure that in the insulating phase, you have a Cooper insulator. So the model can be used, so you can still use a model just for bosons, no fermions around. And this can be done because experimental, you see in this figure here, the resistivity in the insulated phase oscillator with magnetic field, with the oscillation being the quantum, the magnetic flux quantum for a Cooper pair, 2e. So if it was E, then it could be something different. It could be just an electron insulator. That's a particular thing in this model.
That's very interesting. Can I just check? The magneto oscillations you see they are due to Altshuler-Aharonov-Spivak oscillations, right? The phase coherent oscillations.
Well, I think in this system here, they are basically these oscillations basically the fact that the superconductor, when you have the holes here, it is multi-connected. So if you take one point and go around here, the vector potential, there's a contribution from the vector potential, and it has whenever it's multiple of 2 pi, then it repeats itself. and then you get the oscillation.
Yeah.
So it's basically what comes in the exponent of the superconducting order parameter. There is a contribution for the vector potential. Every time that it is around 2 pi, it repeats. Now, this explains the oscillation for integer field. I mean, this main oscillation here. But the other oscillation that you have, like a fractional oscillation, you need to go beyond this thing, is because there is a commensurability effect. These vortices do not fit in the pinning center. So this major oscillation at the zero field can simply be explained in terms of this, it's what we call little parts oscillation.
Yes.
In the past, is basically this effect. Every time you have a multiple superconductor, like a ring of superconductor, you have a flux that's one integer flux you repeat because of 2 pi. But in this fractional oscillation that you don't see here in this particular system, but you see in the others, then you need to take into account that there are many vortices, and the vortices cannot fit in the pinning center. Whenever they don't fit, you have a different local minimum and so on.
Thank you, Professor Granato. That's a very interesting talk. Thank you.
Thank you, Stuart, for your question. The next researcher will be Professor Sergio Conejeiros. Sergio.
Okay, so good morning here from Chile. So thank you for your talk, Professor Enzo. So I'm not expert in your field, but thank you for trying to explain in the best way. So I have some general questions. The first one, so the message that I get from your talk is that as the thickness of the films decreases, so then the transition from superconductor to insulator is favored, right? So
right,
is that
right.
is that a general rule or just
yeah, it's a general rule. Yeah, it's a general rule. If you take a superconducting film and you decrease the thickness, eventually it becomes an insulator. That's that one way of thinking. I mean, in terms of this modeling, it's just because the charging energy increases, but it's actually the transition. Sorry, the transition depends on the ratio of the charging energy divided by the Josephson coupling, right? So you can either approach the transition by changing the charging energy, decreasing the grain size, because this increases the charging energy, the capacitance decrease. Or then you can also approach the transition by decreasing the Josephson coupling. Now, if you think the easy way to think in terms of the experimental in this model is that as you make the film thinner, the amount of superconductivity, the Josephson coupling decrease, the number of Josephson coupling increase, the number of connections decrease, and therefore the Josephson coupling decrease. As decrease, the ratio increase. As the ratio increase, then you go to superconducting state. Because the charging energy is always there, but if it's too small, then you're still in the superconducting phase. But if the superconducting part actually decreases, then eventually the other one dominates. One competes with the other. So in the experimental system, which is not like an array, like a homogeneous film, what happens is that after you decrease the thickness, the system, even though it's homogeneous, is still made of regions, superconducting regions. Not real. It doesn't have to be grains necessarily. It could be just local superconducting regions. And these local superconducting regions are very tiny. They are small. And since you are decreasing the amount of the part that's superconducting, you decrease the connections. Then the charging energy of this contribute more than the Josephson coupling. That's why you get the insulating effect. That's one way to think. But there are other models to describe the thing. But in general, as you said, as you decrease thickness, it will go to insulator. But there are systems that's difficult to see. Before it goes to insulator, something happens.
Yeah. So talking about other models, so you also commented that you need to use a better model, so incorporating a quantum effect in order to to provide a better explanation or to have good results. So the previous model or other model are more classical model.
Yeah.
Classical.
Yeah.
So
Yeah,
we
these
can
models
talk.
charge in fact that sometimes called quantum models, where the others are called classical models. The language is not very good because even what you call classical is a quantum because I mean you do classical mechanics, but you need the superconducting order parameter that only arises because of quantum mechanics. But it's classical in the sense that you don't need quantum mechanics to do like the simulation. But this one you do need to take into account the quantum mechanics to do the simulation.
Yeah, it doesn't have to.
I did actually bypass this thing.
It doesn't have to do with the correspondence limit, for instance, between quantum effect and classical effect. So you call them a classical model, but indeed they have some quantum effect.
It's built in. Yeah, it's built in from the beginning.
Yeah.
To have the Joseph effect, the Joseph effect is a quantum mechanical effect, but you write the equation like the correct classical equation. The current is, is proposed to the sign of the phase difference. The phase are not operators anymore. They are classical quantities. And you can do a lot of this electronic circuits with superconductivity without worrying about quantum mechanics. But the quantum mechanics originate the whole thing.
Yeah. So and I have the last question is about the code that you use for running this simulation. So do you use commercial ones or you are
no. We just wrote
you have your own code. Okay.
Yeah, you don't actually there is no package for this thing because every time you add another term, then who is going to write the package for the whole thing? And I didn't go to details, but most of the work is actually is to do the numerical stuff. The numerical simulation, the Monte Carlo simulation is straightforward in a sense that you can find in many places explaining, but for each particular problem, you have to actually find out the best algorithm to actually, and for this particular case, turns out to be complicated. The traditional Monte Carlo, the simple one, doesn't work well.
Yeah.
You don't get very good data, so you have to go around and modify the algorithm. We did this thing. We didn't have time to explain, but so it's difficult to see a package that will include all these possibilities.
So many years ago, I used a code that I think it was the Alps code, and in that code you have all kind of routine for this kind of calculations. So many Monte Carlo for, but I have never heard about another code doing that kind of.
Yeah, I don't have the experience to use the packages. Every time all the problems that I consider myself, I have collaboration with other people that did the calculation use the package. But all the problems which I consider, there is always a possibility of doing from the beginning, and the codes are not too complicated. Just the problem that the method doesn't work. You have to find the appropriate method because if you do this calculation, it takes a lot of computer time.
Yes.
And then you have to improve the system, find the best numerical. And then when you look at the critical points, the critical exponents, which are basically, which was the main focus of most of my calculation, then it becomes even more complicated because you need a lot of computer time. You have to find what's the best algorithm.
In particular for the frustrated system, the
Exactly. Yeah, there are many algorithms that work extremely well for systems which are not frustrated. For Ising models, XY models, but when you put frustration, then they don't work. And you have to, and that's a pity because you would like to have some speed up of the calculation, but unfortunately, you have to find something else.
Yeah. Okay, thank you very much for your talk again, Professor Enzo.
Thank you.
Thank you, Sergio. Enzo, if you would like to speak more anything, the microphone is open for you.
I'm sorry, I didn't understand what you said.
Your last words.
My last word.
Yeah.
Well, you know, my only last word that I'm sorry that maybe I was not. I mean, I went a little bit over time. I think I didn't have a little bit. I didn't do the summary of the talk, but I wish I had probably more time to describe some of the results. And you know, I thank everybody for staying awake and listening to my talk. And that's the other thing as well. And it's unfortunate that actually when you give this virtual talk, you cannot see the other people. So then it's a bit funny because you seem to be talking to a computer alone. So only after you give the talk that you interact. So that's the way it is.
Thank you again, Enzo. But now we have the last question. Mario Reis from UF, Niterói.
Sorry, I didn't see your message here, Isaias. I never see here the chat.